YouTube. In this video, we're going to bring forth the idea of a compound inequality, okay? And so we've been talking about inequalities last few videos, something like, some 2 times some number plus 1 is less than or equal to 7, and solving them and graphing solutions. But in this video, we're going to talk about inequalities that involve more than one kind of comparison going on. And essentially, I guess we could say this: I could string together as many comparisons as I want here. This would be considered a compound inequality in and of itself. We would say some number 2x plus 1 is less than or equal to 7, is less than or equal to 8, less than or equal to 9. And basically, this would be a completely true statement because we know that these numbers compare the way they do by looking at the number line. But there are 2 particular types of compound inequalities that we see often when you deal with linear inequalities, at least, and those are the and or inequalities. Okay, so a compound inequality we'll define as 2 simple inequalities, where a simple inequality would be anything like x is greater than or equal to 7, joined by and or. Okay, so we'll talk about the difference between and or situations, how they're distinct, and how to tell the difference between the 2. But in terms of solving these, the good news is it is very, very much what we've been working on already. So it says here are 2 examples of compound inequalities. Now what I want to do is this, actually, before we get down to these 2 examples, is I want to graph these. So I'm going to graph the solutions, okay? And of course, remember, we always graph solutions so that we can see how they behave and certain relationships that exist. But, also this, when you sketch a graph in the first place, what you're doing is shading in all of the things that would make this sentence true. And so when we talk about, you'll notice here it says negative 2 is less than or equal to x is less than 1. And there is a difference here. We have less than or equal to on the left and only less than on the right. But we're saying I want to shade in all the numbers that, are to the right of negative 2 or negative 2, but to the left of negative or positive 1. So again, just like with any other problem, we throw a 0 on first, I think most of the time, actually. But we say 1 would be here. We're going to go ahead and label 1, and we're going to say if I went 2 to the left, of course, this would be negative 2 about right here. We're going to go ahead and put a dot on this. Now, what I want to do is treat this like this. Recall that this is a compound inequality. So what I'm going to do is, just for the moment, I'm going to split this up. And I'm going to say negative 2 is less than or equal to x, and x is less than 1. And what I want you to see is this. I've just kind of taken this thing apart and put it into 2 different spots. But if I were to graph these, you'll notice that I would have put a closed dot on negative 2, and it says x is greater than or equal to negative 2, or that negative 2 is less than or equal to x. So this one's going to shade to the right, okay? But at the same time, if I come over here, I say, but x is also less than 1, so it never gets bigger than 1. I would have put an open dot on this, and I would have shaded towards the left. And so you'll notice that they're shading towards each other. Essentially, what we're doing is we're saying it's really just the set of numbers right here, and I'll shade this a little bit bigger. Starting at negative 2 and including negative 2 and going up to but not including 1. And we're going to label this. Of course, you always label your solutions. This is what this is. This is solutions. Solutions, yay. So, what we want to do essentially is this. Recognize this as being an and situation. You notice that I wrote and up here. But make sure that we write and kind of next to your graph on this one, because what we're going to do now is go look at this. Now, or, is this an or situation? I don't know. Well, obviously, I think that we can tell right here that this is an or situation. So what we want to do now is sketch a graph of the solutions. That's what we want. We want to know what would make these true. So again, I'm going to put 0 on here. I think I used similar values here. I say I used positive 2 in this example and negative 1 in this example. But if I graph these individually, which is what I'm going to do, I'm going to say, well, all the solutions to x is less than negative 1. Well, where are the numbers less than negative 1? Well, first of all, put an open dot because we are less than and not less than or equal to. And we say these would be all the numbers to the left of this on the number line. So these would be x is less than negative 1, the solutions to that. And then we say, okay, well, let's graph x is greater than or equal to negative 2. Well, I put a closed dot on this, and I shade toward the right, because what we're saying is this. These are all the solutions to that. So you'll notice that these shade apart. I'm going to make a note about that here. We say shade apart, and that's one thing to note about or situations, okay? Because this is an or situation. And the reason why we say or is because we're saying, well, it could be less than something that is less than the other value. How do I want to say this here? They shade apart because we have this gap in between. So it's to the left of this or to the right of this, okay? But in this case, we say it's to the right of this and to the left of this kind of thing going on, okay? So when we look at this first example, it says solve and graph the solutions for the inequality. And how about we label it too? We label and or. Let's make that the last directive here. What you're going to see is interesting here. Now this is a little bit different from what we just saw up here in graph. You're going to notice that the t is not isolated. Okay, so what we're going to do is this, and it's going to seem odd at first, but we have 3t minus 8 in the middle, less than or equal to 10. What we're going to do is this. We're going to operate on all portions of the compound inequality. The compound ineq. And the reason why is because recall, if these statements are all accurate, and then one of our previous videos we said you could add the same thing to everybody and still maintain equality, then up here we would have seen something like this. We would have said 12 less than or equal to 9 plus 2 is 11, less than or equal to 10, less than or equal to 9, 7 plus 2 is 9, less than or equal to 2x plus 1 plus 2 is 2x plus 3. And so we would still have an equivalent sentence. So in this case, we can just do this. You notice that we have three parts of this. We have the middle, the right side, and the left side. And what we're going to do is this. We're going to identify, first of all, where the t is. We've got them all in the middle, which is a good thing. So we're going to isolate this. So I'm going to add 8. And I'm going to add 8 to everybody. And you need to make sure, by the way, that you add 8 to everybody if you didn't hear me just say that. So 3t, we say, is trapped in between or equal to 10 plus 8 is 18. And then negative 2 plus an 8 would be a positive 6. So we still have an equivalent statement. And again, just like if I were doing equations, solving equations, I'm going to isolate t the same way I would any other time. So I'm going to divide by 3. So I have 6, and we say this is 2. So now, in this case, it's not a word problem, so I can't tell you a label for this. But let's say we were talking about a word problem. Maybe t is time. We'd write, time is somewhere between and including 2 and 6 seconds maybe into some experiment. Something happened, okay? So this last one here, of course, we have an or statement. Oh, by the way, we're supposed to label this one. And, what do we know about and? And graph it. Jeez. But we say and statements shade together. So really quickly, let's go ahead and graph this here. This time a little bit quicker. I'm going to put 0 over here. Notice that t is between 2 and 6, so I'd say 1, 2, 3, 4, 5. We make 5 a little bit bigger, and here's 6. And I'm going to put a closed dot on both 6 and the 2 and label both of these. Always labeling. But I would shade together, okay? It is all the numbers in between here and here that are going to make that true. And then also this last one. The interesting thing here is this. We need to actually solve these individually. So I'd say 2x plus 3 is less than 5. We'd go ahead and start by subtracting 3 from both sides. And we get 2x is less than 2, and then divide by 2. So in this instance, we're going to keep this one in our pocket. We say x is less than 1. I'm going to write or as well. But over here we're going to say, well, then we also had 4x minus 7 is greater than 9. And then we say, okay, well, isolating this, we'd say add 7 to both sides. And we'd end up with 4x. 4x is greater than 16. We'll go ahead and split everything 4 ways. So we get x is greater than 4. So in this case, I'm going to put that there. And so this is our entire compound inequality here. It's these two simple ones. But notice when we put 0 on the number line this time, we go over to positive 1. I suppose I could go further left. Say 0, here's positive 1, 2, 3, 4, 5. We'll call this 5. But here's 4. Here's 1. Looks like we're putting open dots on both. Okay, and then we are going to shade. So we say, well, what if I said x is less than 1? We would be shading to the left of this and labeling it. We say x is less than 1. And we say x is greater than 4. This would be all the stuff to the right of this. We say x greater than 4. So here's our or statement. Okay, and then up here we also should have labeled this, but anyways, that's how you would deal with compound inequalities. You just do the same thing to everybody, just like an equation. So cheers.